Okay, let's go ahead and get started. So um, just as a confirmation, there's the next formal lab is next week, lab 9 and lab 10, the only two labs left over. So this week is meant to provide you some time to work with your group on figuring out what the heck you want to model for your final project and to gather a little bit of data on the input models that you'll be using there. So you don't have to gather all of the data that you need for your final project, but what I'm hoping you'd be able to identify in 1 to 2 pages, and there's some example input modeling reports online, as well as kind of the more detailed rubric, the basic system that you've chosen to study, why you've chosen to study it, what are the kind of fundamental issues with that system that you'll be studying in simulation, and in order to study them, what are the inputs that you're going to need? So what are the things that will definitely be in your simulation model? These are distributions you're going to need to know ahead of time or make assumptions about to build your simulation model. And then what are the control variables? So what are the things that you have control over that you could change, maybe by way of testing hypotheses about the operation of the system? And what are the outputs that you plan to measure from your system? So are you going to be measuring some sort of waiting time at a queue or something like that? How are you going to tell, for one, a topic that we're going to talk about today, how are you going to validate that your model system behaves like the real world system? And then two, what are the performance measures that you're going to take in order to try to then say that, look, if you make this change in the system, it makes a statistically significant change in this performance measure, implying that this change might be worthwhile to make. So those are the things we're kind of looking for, just an outline of what you plan to do. Then after the input modeling report, we kind of leave you alone and you're off to do the project. And then the last week of class, that's when the presentations and the final report are due the middle of the last week of class, that Wednesday. So then you've got a couple of days that you can then watch one presentation and read one report from another group and fill out the peer review. So that's kind of the plan there with the schedule moving forward with the final project and the open labs. So after lab 10, there should be about 2 weeks left. And so we have no labs during those weeks, but so that will be open time for you to work with your group or possibly to work with me or TA in sort of addressing some of these issues or trying to figure out. So some of the things you'll find is that a lot of the basics we've covered on Arena will get you pretty far, but for if you actually are out there simulating a particular system that might have some special feature, you might need to ask me like, oh, is there a special feature in Arena that will make this easier? And I can help you find that so that so there might be some special units that Rockwell has put into Arena that simplifies things, or there's just some kind of component like you'll learn in lab 10 advanced topics about signals and holds, which are really powerful components, which I think a lot of you could probably use to simplify things. And but we don't get to them until lab 10, so you might already kind of be on your way by the time you get there. So so that's something that if you let me know ahead of time, I can try to point those things out. And then also online, if you scroll through the Arena section of the modules, I've got a couple videos where I've got kind of some other hints and tips on special things you can do, like kind of pool logic and things like that, where you can have people waiting in a queue until something happens further down the line, and then it'll pull them out of it. Or you can have things conditioned on what's happening in the queues, and so you can have, does somebody wait based on states of other things in the systems? And so I've got a couple of examples where I've kind of pulled in what are slightly more advanced, but I think very realistic cases that you'd see in like airports and such things like that. So take a look online and maybe those will give you some ideas. So yeah, the final project, it's kind of all I've kind of summarized here. Like I said, input modeling report due Sunday. It's a group assignment, only one person has to upload it. It's hopefully then I will go through and read the 11 or 12 input modeling reports and give you guys feedback on, it sounds like a great system. Here's where I think some of the red flags are. Here's what you should watch out for. The biggest thing that I'll be looking for is if you've picked a system that looks like it's kind of too simple for simulation. Like if you just pick something that's a single channel queue, well, that's something that would be a node in a simulation, but not something you'd simulate yourself. And so if with there already are techniques to do analytical work that you can sort of answer with a little bit of mathematics what goes on in these sort of single channel queues. And so what we're looking for in simulation is you build a sim when there's really no easy way to use the math to answer those questions. And so you really need to build a kind of simplified but still complex version of your system in a computer and experiment with it, because you can't go in and do the math. And so you're kind of looking for. So you want to be a little more exotic. It doesn't have to be super complicated, but at least has to have enough moving parts that would make it really difficult to answer questions about using any other methods. Other things, ICAs continue to, to be available. There's only a couple more left. ICA-L is the last kind of new ICA, and then ICA-M is the final review ICA, similar to the midterm ICA. Homework G3 is online. Question 1 is basically a chi-squared question, where you have to do a chi-squared analysis with the parameter given and also without the parameter. And then question 2 is a power analysis problem. And then there's only one more homework left, and that homework will actually involve ARENA. So it'll feel a little bit closer to the labs than the previous homework. So any questions about things moving forward? So the question was, can you use jump on the chi-squared test for the homework? For this homework, I want you to be doing it. You need to do it by hand, or show me that you can do it by hand at least once. So I know you've done plenty of chi-squared classes or chi-squared tests by hand in other classes. It's a relatively, you should be to the point where a chi-squared test is so easy to do that it's not, that it shouldn't feel like a major ask to do one. And at that point, then we'll say, okay, now you can use jump. But if you're not at that point yet, we still want you to have practice with that. So this question here, I'm going to want you to practice. And I'm doing that because I want to make sure everybody understands what happens when, say, you have to put two bins together because there's not enough expected counts. So we really want to make sure you feel in your heart what it means to be a degree of freedom in a chi-squared test. And at that point where you've made all that, brought that in to yourself, and that's become a lot of intuition, then it's okay to use jump and things like that. So of course, for your final project, I'm happy you to use all those statistical tools, but for this homework, I really want you to do it by. Okay. Question online, how complex does the system need to be? There's a question online. There's not an easy answer for me about how complex the system has to be for the final project. It's that heuristic that it needs to be interesting enough that simulation really seems like the only way you could easily answer that question. So if you're saying, I want to see what happens to the amount people wait in line if you double the number of servers, well, that's not that interesting, because we probably could get a pretty good answer to that without even simulating a system. So if you know that they're coming in with exponential interrivals, you've got a Weibull service time distribution. If you just change the average of this, or if you just double the number of servers and you keep it Weibull, then you kind of know you might like have the time or something like that. Or you could use some heuristic, maybe you could call on Little's law or whatever. Like there's a bunch of things you could do without even having to simulate it. So the simulation things comes into play when you want to, change the architecture. So I went from this particular assembly style to this other assembly style, where there's no formula for this particular type of assembly, and so I have to just build it in sim and see what comes out of that. A group asked me about an intersection problem that they wanted to work on. I just thought it sounded great, where it was about adding stoplights or stop signs or crosswalks to a particular intersection and studying the effect of those. And that is an interesting, complex problem, because you've got cars and people arriving in different directions, all trying to make use of a single resource. And while anyone's using that resource, no one else can use that resource. And so it's not, there's not a simple sort of in and an out. There's multiple inputs and multiple outputs and the mixtures of those two, and that's what makes it kind of interesting and complex. But it doesn't have so many parts that the ARENA diagram will be very big. It just has enough parts that we can't really reason about with anything other than simulation. So I know it's a little bit hard of an answer, and that's the reason why we're submitting these input modeling reports, so that I can have a quick look at these things, so that I can help you and say, you're on the right track with this system, but maybe you could consider studying this aspect instead of this aspect. That seems to be more appropriate for sim. So I will try to help you with that as I get your input modeling reports. And also note that when your input modeling reports go in, I'm not going to check whether they match up with what you finally submit as your final project. So you might decide on the system, submit the input modeling report, and then decide, you know what, this isn't really working for us, but oh, there's this other system we didn't think about, and then you can switch to that, and that's fine. I just want to make sure you've built up some momentum on some systems, so you've got a plan A that so that I can let you go until now into the end of the semester and feel confident that you've at least got a next action to take. Okay. Any other questions? Also, I'll look online. Sorry, I caught that question a little late online. Okay. All right. So let's do an early attendance exercise that we're already pre-prepared here. So I'll put the URL in the chat as well. So just to warm people up a little bit here. So I got a little fill in the blank here. And the prompt here is I should be most suspicious of blank p-values when I have blank number of samples. And so I'm asking you to select the answer or answers that would properly fill this in here. So take a second to submit what you think. You might say A, you might say A and C, whatever you would like. Put that into your attendance prompt here. So again, the question is on the slide. And then let's just go down through and see what people think here. So how many people think it is, well, I guess I could say rather than well, it might be kind of worthwhile. If you're online, I'm gonna basically go through A, B, C, D and poll people and see how many people think they're each one. And if you're online, then maybe it'll be easier for you to then put into the chat when I go, well, what answer you think they are. So you can tell me online what your answer is. You can put it in the chat. And then in here, I'm just gonna ask for hands and then I'll kind of aggregate those. So how many people would say that A is an answer to this, low and small? So in low p-values, small numbers, okay. How many people would say B is an answer to this by hands? High p-values, large number of samples. All right, what about C? Low p-values, large number of samples. All right, I've got a lot of hands for that. And what about D? High p-values, small number of samples. I've got a couple of hands for that. See online here. So in class, I got a lot of C's and a couple of D's. Online, I got the same distribution, a lot of C's, a couple of D's. And that is actually, I'm pretty happy with that because the answer that I was looking for was C or D. So low p-values, you have been taught up to this point that low p-values indicate you should reject the hypothesis. And a hypothesis is usually a null hypothesis, which is usually the status quo, sort of what's normal. So what hypothesis testing is trying to do is detecting a deviation from the normal. The fancy word we use for normal is null. So when you have a low p-value, we say, you've detected a deviation from normal, but you should be suspicious of that when you have a large sample size, because the higher the number of samples you get, you can always detect a deviation from normal. Normal is an ideal, and the real world will always be somewhat different from normal. And the larger you make your samples, the easier it'll be to detect that deviation from normal. So you should be suspicious of large p-value or low p-values when you have a high number of samples. And you should ask somebody, okay, great, you've shown a significant difference, but what's the effect size? And that effect size is something that you're going to start seeing on question 2 of your homework. And so the question is, great, it's statistically significant, but is it practically significant? So is the deviation from normal large enough for me to shut down my operations and redesign everything? Then the other one was high small. So when I have high p-values, I should be suspicious when there's few number of samples. And so this is for goodness of fit. So if you have a high p-value, people might say, aha, that is evidence for the normal, for the null. So a high p-value might be saying everything based on these data, we can just assume the null hypothesis is correct. But if you have a small number of samples, then the smaller the number of samples pretty much start accepting every hypothesis. And so if you only have one data point, you can't really discriminate among almost any hypotheses unless the prediction of your hypothesis is that you will never, ever, ever get that particular data point. Then you can maybe discriminate those. But most hypotheses have predictions which have a full spread of possible answers. And your answer that you found in your one sample is going to fit into them. So in order for us to assess how likely a hypothesis is, we really need more than one sample. We probably need more than 5 samples. So a high p-value just means that if that hypothesis was true, then we could get a measurement that was like this or even farther away. But for a small number of samples, we'll always have high p-values or higher than 0.05. So suspicious of high when you have small, suspicious of low when you have large. That's something I want you to burn into your brain. So any questions about that? Okay. All right, let's do one more. So again, I'll put the link in the chat for convenience. And the question is on slide. And so go ahead and submit what you think here. A test with higher statistical blank will reject a false hypothesis with fewer samples. So if I have 2 statistical tests that are legal for me to apply to my data, I'm going to say that the one that has higher statistical blank, so there's a term that we use there, it will reject a false hypothesis with fewer samples. And so it's somehow more sensitive. So what is the term that I use there? And if you have a guess for that, you can feel free to raise your hand or you can put it in the chat. Does anybody have a guess? Yeah. Power. How many other people thought that power was on their mind, at least as a possibility? Okay, there are a couple. Online, I've got a couple of power there too. Power was the answer that I was looking for there. So you guys have learned the definition of alpha, type 1 error. And that type 1 error is like the probability, that's the, it's the error rate. So it's how often you reject a null hypothesis when the null hypothesis is true. Statistical power is a little bit of a flip side of that, where this is it's actually a probability of rejecting, well, I'm not going to define it formally here, but things with high statistical power will tend to be able to reject a false hypothesis with fewer samples. And so the flip side of that is things that have high statistical power, you can actually accept hypotheses with fewer samples. And so you might say like a Chi-squared test is a goodness of fit. That's me. I have somehow triggered. I apologize for that. So a Chi-squared test and a KS test are both good goodness of fits tests. But we know that if you have few numbers of samples, they'll both have relatively high p-values. That just happens. As sample size goes down, p-values go up. So which one can you trust as a goodness of fit measure? The one with higher statistical power is the one where if you have very few samples, you might still be able to trust the high p-value. And a KS test has higher statistical power than a chi-squared test. That's one of the reasons why if we have 5 samples or something like that, and we do the KS test, then if it comes up with a p-value greater than 0.05, we'll say that's a good fit. But if it's a chi-squared test with few numbers of samples, we might say we need to get more samples to evaluate this fit. So high statistical power allows you to assess the acceptance, I guess, of a hypothesis with fewer samples. All right, any questions about that? Okay. All right, so these are our formal definitions. We've got this alpha, the significance level. That's the type 1 error rate or the false positive rate. We're going to use the term positive as detecting a difference from the null hypothesis. So again, the null hypothesis is kind of what we assume would be the normal case if nothing exciting was happening. And if someone is trying to convince us that something exciting is going on, then they've got an alternative hypothesis. And so in order for us to find support for their alternative hypothesis, we need to reject the boring case, and that's the null case. And so the alpha is our assuming the null is true. This is the probability we will accidentally reject it. And so we talked about this last time. If a test has alpha equal to 0, you don't reject anything. If it has alpha equal 1, all hypotheses are rejected. And then the p-value is related to that, where that's actually the probability of the observed deviation if we assume the hypothesis is true. So again, if we assume that this is the normal case, the null case, we could say, well, and we got these data, we'd say, well, if we look at the distribution of data we could have gotten under the null, then how often would we have gotten these data or data even farther from the mean or even farther from the center of that distribution? And that is the p-value. So to get a statistical test meeting the alpha, we can just make alpha the threshold on the p-value. So if we say, if we calculate a p-value, which we can do as long as we know the distribution of things that come out of the null, then from that p-value, we can say, does the p-value, is it less than alpha or greater than alpha? And if we use that as our decision criteria, we will meet the error rate assumptions up here. That's how we build tests with programmable error rates, is by base them on p-value. So that's that half of it. That should all be reviewed. The other half that may not be as much a review is the type 2 error, the beta value. So we have this thing called beta, where if we assume the null hypothesis is false, so we are in a special situation that's different from normal, then what's the probability that we will fail to reject the null hypothesis? So what's the probability that we will still conclude that we're in the normal case, even though the world is weirder than normal? And that would be a type 2 error. And that's what we call beta. It is harder to calculate type 2 error ahead of time because it's easy to assume a null distribution and use a little bit of math. We can say under the null hypothesis, all of our predicted outcomes would fall under a normal distribution, and we can calculate things under normal distribution. But when you say the null is not true, you say, well, then what is true? And so you don't often have an analytical grasp on the distribution of what the outcomes would be if the null isn't true. And so this is a much harder thing to calculate or reason about. Now, the statistical power that I was just talking about is just 1 minus the type 2 error rate. So when I'm talking about power, I'm just as well talking about type 2 error. High power is low type 2 error and vice versa. It's just a 1 minus relationship. Or put another way, given that the null is false, given that I'm in a world that's not the normal case, what's the probability that I will actually properly reject the null? So statistical power is the probability of doing the right thing. So you could call up here, so you can think a negative, that's failing to reject the null. We'll call that a negative result. So you can call this a false negative rate. And the statistical power, another term for that is the true positive rate or sensitivity. And so we've got the false negative rate, the false positive rate here, that's alpha, and power is the true positive rate. So that's why these two things are often talked about more than alpha and beta. It's usually alpha and statistical power, because that way we can phrase everything in terms of positive rate. So we can talk about the false positive rate and the true positive rate, alpha and power. So those are the two things there. If a test power is there's two things that affect the power of a test: the number of samples, which we've talked a lot about so far, but also the variability of the data. if your data are not very variable, if they're pretty much consistent, they always come out the same result, then you don't need many samples to get high power. Because once you take the first sample, you pretty much can make an inference where you know what the rest of the samples are going to be. But if there's a lot of variability, you have to take a lot of samples just to get an idea of what the kind of average value is. So if the more variability means you've got to have more samples to get power, the less variability, you need less samples to get the same power. So power is determined by these two things. And so a power analysis, like the one you'll do on the second question of your homework, can help you determine either the number of samples you need to meet a particular power constraint. So in other words, to detect a difference of a specified size, or given that you're stuck with a certain number of samples, it will allow you to tell you what's the biggest difference that I can detect with that number of samples. And so the idea would be like the World Series, for example. So only going to play 7 games in the World Series. Nobody's going to watch more than 7 games of baseball. And so you could say, well, we would like to detect whether which of these two teams is the better team. Well, if we really wanted to detect which of these two teams were the better team, we would have to define what it means by better. And that would mean that, well, in 55% or more games, this team would win. So that would mean we'd have this effect size, which is somehow like 5%. And so then we'd say, well, then how many samples do we need to be able to detect whether there was a 5% difference? And so, there's maybe with only one sample, we could only detect if there was a 40% difference between the teams. With 2 samples, we can cut that down. Eventually, we get to a certain number of samples where we can detect a 5% difference. Less than the 5%, we can't detect that. So if one team would only win 52% of the games, that would be such a small difference that we would need more samples to detect. And so in the kind of World Series case here, we can't play more games, but we could ask, given a particular, how different would the two teams have to be for the World Series to be able to actually detect which one was better? And that would be something that we could answer there. So it's one of those two things here. How many samples you need to detect a small enough difference, and you have to define what it means by small enough, and that's what you'll do on your, this is like the second question of your homework. Or the flip side of that, if you're stuck with a particular number of samples, what is that gap in difference between the two hypotheses that you'll be able to detect? And anything under that gap, you won't be able to detect. So hopefully this will become more clear as you do that homework and as we move on. And actually, we'll get into this in a little bit more detail on Thursday. Thursday is my Halloween statistics lecture, where it's always significantly spooky. It's filled with a lot of those types of puns, but we'll talk a little bit more in detail about all this kind of pure stat stuff and how it relates to the class. And one of the things that we'll get into more detail is this curve, which is called the ROC curve, the receiver operating characteristic curve. It's called that because it originally, when they first came up with radar, they just had radar operators, humans, sitting and analyzing radar data as it was coming in, and they could test those humans and how good they could detect whether they've actually seen something on the radar that's a real thing. And then they could assess the false positive rate and the true positive rate of each one of these humans, and they would get these curves where those who had a particular false positive rate, you could then say, well, what was the corresponding true positive rate? And the farther you could get off the diagonal, the better of a receiver, a radar receiver you were. And that's where this term receiver operating characteristics curve is. So a good, someone who does very well operating the radar is going to have this curve that'll be kind of way up here close to the kind of top left corner. And a really bad radar receiver is going to just do as well as chance, which will be the diagonal line. So this you can apply to any hypothesis test. And so, for example, we could build a hypothesis test where you just flip a coin and you see whether that coin is less than or equal to alpha. And that hypothesis test will be the diagonal line here. So if alpha is equal to 1.0, then it will always come up true, I guess. And so your false positive rate will be 100%, but your true positive rate will be 0. Likewise, if you set alpha equal to 0, that coin, that if you flip the coin, it'll never be less than 0. So the false positive rate will be 0 because it'll never detect a positive, but the true positive rate will also be 0. So just changing the threshold for a random number generator, when I say flip a coin, I'm saying like a weighted coin. So if my random number generator is generating numbers from 0 to 1, changing the threshold of what I'm calling true gives me this diagonal line. That is my crappy hypothesis test. And any good hypothesis test will have a trade-off curve that will sit above that. And these, for example, are 3 hypothesis tests that come from machine learning. Doesn't matter what they do, but my point here is that if you dream up a classifier in machine learning, you test it both of these ways, and you evaluate the strength of your classifier relative to another classifier based on how far away from this line they are. So you can take the area underneath this curve, and if the area underneath this curve is larger, then you've got a better classifier. It's like a better radar receiver. So this ROC curve is a curve that if you go into data mining, if you go into machine learning, then you'll become very familiar with these curves, but they just capture alpha and power. So that's why these are 2 things that you should become very familiar with, alpha and power. Or false positive, true positive, another way to say that. All right, so questions on the ROC curve. Just want to give you exposure to this, and we'll see a little bit more about where this trade-off comes from on Thursday. Okay. All right, so last time, talked about summary statistics. I know you guys probably gotten this a lot, so I'm not going to go into a great deal here. My biggest point here is that a summary statistic is not a parameter of a distribution. It is just a property of data. What is the sample mean and what is the sample variance for the data? The true mean, the true population mean, you don't know, you're estimating it. So if I'm treating this as an estimate of the population mean, I'm going to need to put confidence intervals around it. And we will get into interval estimation next week. And that's where we start defining what it means to be a confidence interval. So for now, they're point estimates, and nobody likes point estimates, but we have to start somewhere. So the point estimate of the mean, the point estimate of the variance. Big thing about the variance, you divide by n-1 when you're using the sample mean to calculate the variance. So you usually don't have to calculate this, but you should know that whenever you ask Excel to calculate variance, it's dividing by n-1. So if you know the actual mean and you provide it to Excel somehow, then you need to tell Excel to divide by n, and there's a flag to have it do that. So any good statistical program out there, when you ask it for variance, will be divided by n-1 because they will estimate the mean. So if you, for some reason, don't want them to divide by n-1, you have to then set a flag, and then they'll divide by n instead. You can do the same thing with discrete random variables, but the formula changes a little bit. You take every outcome, and you multiply it by how frequent it occurred, and you divide that by the total number of samples. Similarly for the variance calculation. And if I just give you a histogram of continuous data, you pretend like it's discrete, and you use the midpoint of every bin of the histogram as your discrete outcome, multiplied by the frequency of that bin, and that's how you calculate the sample mean. Same thing with the variance. So any questions on this, the sample mean and sample variance? Again, hopefully just review of old stuff here. I'm not going to force you to calculate a lot of means. In fact, if you need the mean for anything on a test, I'll just tell you the mean, because I'm pretty confident that you could do this calculation if I asked you, but still need to know how it's done. All right. So what about parameters then? So we've got a distribution. We say we definitely want to pick an exponential for the interarrival times for people that arrive to this door. So what's the best parameter to use for that exponential distribution that I'm going to plug into Arena and tell Arena, start drawing interarrivals from that? I got these data, what do I do? Well, the maximum likelihood estimator is a great place to start with that. And the idea behind maximum likelihood was that you can take a probability mass function or a probability density function, you can plug the data you have in as if they were parameters and use the parameters of the distribution as those free variables, and then just maximize the probability mass or the probability density to pick the best parameters. So we did that with the exponential, and what we found is that the best rate for an exponential is just the reciprocal of the sample mean. And so if you did want to fit an exponential, just take all of your data for your inter-arrival times, take their average, get the average time in between arrivals, take its reciprocal, and that's the rate that you plug into ARENA. I actually think ARENA asks you for the average, so you would actually plug in the 1 over, or sorry, you plug in the X bar here, because it will do this for you. So in ARENA, they say, what do you want the average inter-arrival time to be? And you plug in the average. But if we're actually writing out the PDF here and figure out what to write in the PDF, the parameter we need in the PDF is this lambda, which is just 1 over the sample mean. And we get that by doing a little bit of calculus. And if we did that on other distributions, we could do the same thing. For Poisson, the best parameter is the sample mean. This was the example I had last time, is in the Poisson, you could use the variance as a parameter estimate here, because in the Poisson, this parameter is also equal to the variance. But the maximum likelihood estimator is specifically the sample mean. So we always use the sample mean to estimate this, even though maybe you might think that because theoretically this parameter is also equal to variance, we could use the variance as an estimator. The best estimator is the sample mean. And then likewise, you can look up formulas for other distributions. So I just provide this table here to say, for any distribution that's out there, before you start doing a lot of work on your own, just Google for what is the maximum likelihood estimator of a Rayleigh distribution. And then hopefully somebody already got that for you. They'll give you a formula that'll probably have the summary statistics in it. Plug the summary statistics in, and you're off and running. You can now generate your Rayleigh distribution inside ARENA, and you didn't have to do any extra math. So these are just a couple I provided that were in the book, but you could imagine any distribution. So that's the key word you want to take out of this, is maximum likelihood estimation. So MLE. So I don't know what the parameter is going to be. What's the best MLE for this distribution? Questions about that? About the maximum likelihood? This also, I think, should be reviewed. I think we do MLE in 380. I always get mixed up what we do in 380 and 385. Yeah. Well, I don't mean by hand. I mean, like, you could. So I don't have. There's not a lot of value to me for this class. For me to, I'm not going to ask you to calculate, like to do the calculus to solve for this. But I may ask you about an MLE. Like, I want to make sure that you know that if I were to give you a distribution and you needed to fit that parameter or find that parameter, that MLE would be one way to go. Okay. All right. As I hope you'll see, I heard some conversations earlier in the class about some other classes and things like that, and like, what throws you for a loop or whatever. Like, the math seems like it's the hardest part, but once you get used to it, it's like the most routine part. The hard part in all of this crap is figuring out when to use the right math, right? So it's more about knowing that I even need a maximum likelihood estimator. If I tell you you need a maximum likelihood estimator, you're good, you're golden. I know how to do that. And knowing you need it ahead of time, that's the really hard stuff. And when you go to interview for things, I mean, I had interviews coming out of undergrad where I did have to do stuff like this, like manually derive things and draw circuits and all that sort of stuff. But the hardest questions really were, trying to justify my answers. Like, why did you use this? Why did you use that? Why didn't you use this other estimator? Those sorts of things. Those are the things that we want to try to really teach you guys. But that's the hardest stuff to teach. So yeah, I don't care that much if you know how to calculate this. Although I have a feeling that if you wanted to figure out how to calculate this, you'd probably have that would be very easy to do. But I definitely want you to know about the general process. All right. Okay. Any other questions? Nothing online? All right. Let me skip ahead to some stuff that we missed last time, just the updates on the goodness of fit tests that you'll need for that homework. So Chi-squared test, and this should, I think, probably also be review, but we did the Chi-squared test for uniformity before the midterm. Now we need to apply it for anything. And so the basic idea here is that for any distribution I ask you to calculate a goodness of fit for using a chi-squared, you can cut the range of values that you see in the data up into bins. And then you can ask, if this was a certain distribution, a Poisson, how many would I expect to be in each bin? And then I can say, how many did I observe in each bin in the actual data set? And then I can calculate the chi-squared, the same way we did pre-midterm. And so the only real difference here is that sometimes you need to do a little bit of math to calculate what the expected number is that goes into each bin. So you need to calculate what's the probability under the under the hypothesis I'm testing that that points would fall into that bin. And that's something you might need to calculate. You take that probability, you multiply it by the number of samples observed, and that gives you the expected number for that bin. So in the uniform distribution, it's the same across all the bins, but in general, each bin could have a different expected count. Now, once you've done all of that, and if I give you, let's say, the CDF, then you can just use the CDF. You can evaluate the CDF at the edges of the bins, subtract the difference, and that will give you that probability. Now, once you've done all of that, there's going to be some bins maybe that have an expected count less than 5. You cannot, and we'll talk about that, I think, next time, why this is the case, but you cannot, next time, you cannot do a chi-squared test if one of the expected bins has less than 5 in it. This doesn't meet the assumptions of the math underlying the chi-squared test. And so you have to combine bins. Your goal is to, at the end of the day, have as many bins as possible, but none of the bins should have less than 5 in them. So you combine adjacent bins to make that happen. And you'll have to do that in 2 different ways in the first question of the homework. And so, so that's kind of all that I'm sort of saying here. And then finally, once you've calculated this chi-squared, it's all the same as pre-midterm. You look up in the back of the book for the right critical value. The only thing that really changes here is now the degrees of freedom is a little different. Pre-midterm, it was 1 minus, or was 1 fewer than the number of bins. If you had 5 bins, it was 4. Now it's the number of bins you have minus 1, minus the number of estimated parameters that reduce the degree of freedom. So if you estimated the mean, that reduces the degree of freedom. If you estimated the variance, that reduces the degrees of freedom. So the number of parameters you estimate that are based directly on the data, you have to subtract that from your degree of freedom before you look up the critical value. So I can, I think I can show kind of an example of that, or the reasons before that. So like, this is the kind of the degree of freedom slide here. So in order to calculate the mean, you have to sum up all of the data. And we know that the number of observations kind of all sum to n. So, all right, well, so this is the reason why it starts at n-1, because once you know the observed counts in all n-1 bins, you automatically know the observed counts in the last bin. That's the reason why you start at n-1. But if you then also estimate the mean and estimate the standard deviation or the variance, that's another formula where once you know that estimated mean, then you need to know less about your data. So it's kind of like if I tell you n-1 points and the mean, because the mean was calculated with all n points, I've effectively told you the last point as well. So every time you estimate a parameter where you have to put in all of the data to calculate that estimated parameter, you necessarily reduce your degree of freedom by 1. So that's the reason why together you have a degree of freedom equal to the number of bins minus 1. That's just because of the sum, they all sum to n, minus the number of estimated parameters. And that is what you're going to end up looking at in the back of the book for your chi-squared critical value. And so if after all of that, you get a degree of freedom equal to 0, which you shouldn't, but if you did, that's the so-called overfitting case, where effectively you've loaded up all of your data into parameters. And so you're going to get ideally a perfect fit, because there's no degree of freedom left over. So that's why we want these degrees of freedom to be as high as possible, because that gives us kind of more statistical ability to analyze these things. All right, so I think these are just a couple of examples of, like, for a normal distribution, if I estimate so I'm saying, like, if evaluating a normal distribution and I don't give you a mean and standard deviation, then you have to estimate the mean and standard deviation. So the degrees of freedom are going to be n-3. So however many bins you have -3. It's the original one minus the 2 parameters. But if I instead say, hypothetically, these data are from a normal distribution with a mean of 5 and a variance of 2, these aren't estimated from data. These are part of the hypothesis. And so for here, the degrees of freedom is just n-1. Now, parameters that do not involve plugging in all the data to estimate don't diminish the degrees of freedom. So if for a uniform distribution, you might look at the values and you'd say, well, the lowest value is 0.5, the highest value is 7.5. So I'm going to estimate a uniform from 0.5 to 7.5. Well, I didn't have to plug in all of the data to get that 0 and 7.5. So these two parameters, these two shape parameters, did not actually decrease my degrees of freedom. So for these kind of usually shape parameters that you don't plug all of the data in to guess, they don't have an effect on the degrees of freedom. So are there questions about these examples? The question where, so here, the estimated case, the not estimated case, or the types of parameters that, even though you estimate them, don't reduce the degree of freedom. So these three categories make a little bit of sense. Also look online to see if there's any questions. Anybody? Does that seem pretty clear? All right. So this was just the example before the midterm, where we calculated the expected number was 7.5. And so we know how to do that from before the midterm. How do we calculate the expected value for an arbitrary distribution? This is kind of what I hand waved through before. Just calculate the probability that things landed in that bin, multiply it by the total number. So if it's a discrete one, like your homework, where it's a Poisson, you can say, well, this bin is anything from 2, 3, or 4 counts. Well, I can plug in, well, okay, what's the probability that I would get a count of 2, a count of 3, a count of 4? And I can add up all of those and multiply by the total number of samples. And that's the probability that I'd be in a bin that has 2, 3, or 4 counts in it. For a continuous random variable, I've got to take the integral from the lower end of the bin to the upper end of the bin. And if I'm provided the CDF, then I just can evaluate the CDF at the upper end minus the CDF at the lower end. I think I've got an example of that here. So, so this is our case, we purely are continuous. And so it's this top one up here, where if I say, all right, you've got an interval from A to B, then I can just do the CDF at B minus the CDF at A. That's how I can get that probability. If I don't give you the CDF, then I thought I have an integral. Yeah, then I have to actually integrate under a curve. So like here, if I'm told that if I wasn't given the CDF for an exponential, and I'm given this this question here, X is hypothesized to be exponentially distributed with a known mean, n observations are binned into 10 intervals, then I can say, well, I'm asking what the degree of freedom is here, but I just want to move on here. What's the expected number that land inside a bin? Well, if the bin goes from 2 to 3, then I have to integrate under the PDF from 2 to 3 to give me a probability. If I know the CDF, I could evaluate f of 3 minus f of 2, and I get a 14.5% probability. Multiply that by n, and then that will give me my expected count. So that's how we calculate in general the expected counts for a chi-squared. Does that make sense? Are there any questions about that? You'll do that for the discrete case on your homework. Okay. All right, now the other one that we have to cover is the update to the Kolmogorov-Smirnov test, because what you might find is that I've provided you so little data that the only way you could bin everything together is by making like one bin that has all the data in it. At that point, you can't discriminate among any distribution. So an alternative to the chi-squared when you have low numbers of data is the Kolmogorov-Smirnov test. So for small sample sizes, we can use the KS test. Before the midterm, this is how we did the KS test. I would give you data points, and I'd say test them for uniformity. And you'd sort them, and then you would calculate how far are they from their two bin boundaries. And so, or in other words, I would expect the first data point to be anywhere between 0 and 1 divided by n. I'd expect the second data point in the sorting to be anywhere from 1 divided by n to 2 divided by n, and so on. And that's how we would calculate the KS test. For a general distribution, it's almost identical. I'm going to give you the data, and then what you do is you plug the data in to the hypothetical CDF. And that's what I've done here. So I've given you data points X, and then I plug them into the hypothetical CDF that I'm testing, and that produces numbers between 0 and 1. And then I pretend like I'm testing for uniformity. So a Kolmogorov-Smirnov test, a KS test for an arbitrary distribution is identical to a test for uniformity of data that's been mapped through a CDF. So I want to, if this has a good fit, then after I map the data through the CDF, I should get a set of uniformly distributed numbers coming out of the CDF. If I don't, then the KS test will detect that difference. So if I plot that not in the kind of CDF space, but in the kind of data space, then what I'm really doing is I'm comparing the sample CDF, which is just the sorted values plotted against their rank, times or against the hypothetical CDF. And I'm looking to see how far apart they are. And those differences go into my Kolmogorov-Smirnov calculations. But notice the calculations here are identical to the calculations you did before the midterm. Just instead of the data point, it's the data point when it goes through its CDF. And this generalizes to uniformity as well, because the uniform CDF is just the identity function. It's just a ramp. And so if I put in the CDF for the uniform here, it will just give me right out whatever the input is. And so it becomes this test for uniform. So any questions about this process? The KS test is just the same thing you did before the midterm, but you take the data points and you run them through the hypothetical CDF first. And then you do exactly the same thing you did before the midterm. That's the KS test for any distribution, not just for the uniform distribution. And that's what's going on behind the scenes in ARENA when it's calculating that too. All right. So the KS test is a great test, but there are more powerful tests. We won't go into it in any detail in this class, but you might see them pop up just as you move forward. So one of them is a popular one is the Anderson-Darling test. This is a more sophisticated test to calculate the KS test, but it is more powerful. So more powerful tests are goodness of fit tests. Remember, power is all about type 2 error. Goodness of fit is all about type 2 error. If you want to get rid of your type 2 error, you increase your power. So if you want to say these data are consistent with a distribution, you start usually with things like chi-squared and KS and Anderson-Darling. So Anderson-Darling is a much better test than the rest of these if you can calculate it. And then if you really want to go for a particular distribution, you look for distribution specific tests. So there's a bunch of times where you need to test for normality. I could use an Anderson-Darling or a KS test to test for normality, but it's better for me to use a so-called Shapiro-Wilk test. This is a goodness of fit test that only works for normality. And so this has extremely high power. So you can test for normality with very low amounts of data, but it only works for normality. So I'm not going to go over how to calculate this, but if you're ever in a position, now you'll find if you go on to future stats classes, you will often have to show that the data going into your stats are normally distributed. And the way you typically do that is with a probability plot to start with. But then after that, somebody's going to look for a Shapiro-Wilk. Shapiro-Wilk tests for normality and only normality. It's the best test for that. If you want to test for something else, Anderson-Darling's great. If you want to test for normality, go to the Shapiro-Wilk because it just has so much power. All right. And then, like I said, couple that with your probability plots, your PP plots and your QQ plots. And if everything falls on a line and is failed to be rejected, then everybody will be happy. Because again, it's really hard to say, it's really easy to make type 2 errors. These high-powered tests generally don't make type 2 errors, they still can. You couple a high-powered test with a probability plot, and you're golden. You can really say, it is okay for us to assume that these data are normal, that these data are exponential, and so on. Okay, so any questions about that? That was our goodness of fit stuff. Good, okay. All right, so the rest of what we have today is just opening up our section on validation and verification and calibration. So we're getting kind of back to the simulation stuff. And so we know that you got input models that you're going to start working with. You put them into your simulation, you get variation on the output. We know that if you choose bad input models, you're going to get variation on the output, but it'll be bad output. So you can't really make any good inferences that regardless of how good your model is. And so after you build your model and put your inputs in, a nice test to make sure you made good choices everywhere is to compare your output to realistic output and see if you have so-called validated your model. So that's what we're talking about here is we're looking at the validity of the inputs, and we're doing that by testing how well the output variation looks like real world output variation. So there are three terms that we throw around here. Verification. Verification is basically debugging. Did I implement what I said I was going to implement? And so for verification, you take stats on input models that you've implemented inside Arena just to make sure that you put in an exponential with a particular mean, it actually generated data that looks like an exponential for a particular mean. That's verification, just debugging. The next step is validation. Validation is, are my model structure and assumptions correct? So once you've verified that there are no bugs in your code, does the output variation that I get match the output variation that I would expect out in the real world? If it does, then I've validated that I have a good model, a good surrogate for the real world. Now, what you often find, well, you might find they're totally different, in which case you have to go back and make major changes to your model, or you might find that they're a little bit different and you have to kind of tune a few things to get them so that the outputs match the outputs in the real world. That process is called calibration, which is improving the caliber of your model, calibration. So those three things kind of go together. You do the verification to make sure you can do the validation. Validation is an assessment of your model. Calibration is going back in to hopefully make it so that the validation step shows that your model is a better fit. So that's kind of the three things that we cover. And so we often refer to these together as V and V. So that's what I kind of got up here, V and V. That's kind of the industry term for this. Some people also refer to it as TV&V, testing, verification, and validation. So TV&V looks a little bit like this. It's basically just a diagram saying the same thing I already said. This comes out of your book. And so you've got the simulation model down here. You've got the real system up here. You look at the real system, you come up with a conceptual model in your head. Like, I think that if I combine an exponential with this, with that, if I put things in this order, I should get something that captures all of the important features of the real system. You build it in your computer model. You do verification to make sure the computer model matches what's in your head. And then you do calibration and validation to then see if the computer model that's in your head produces data that actually looks like the real system. So that's TV&V right there. And then this calibration loop here is just constantly comparing the model to reality and revising. And so the calibration process is just all of these steps. So this is kind of showing it in time, and this is kind of just showing it statically. But that's how we use those terms, TV&V. And so what we're going to be talking about in this section is how do we use statistics to rigorously compare the input and output relationship in the model to the input-output relationship in the real system. That's kind of the biggest thing that we do here. I'm going to show you tips as well about how to better debug your ARENA models and things like that. And I'll kind of flag points where we took data here because this data would be useful for showing that our model's built correctly. But most of this section is about using stats to compare real world data to the data that's in our that's coming out of our model. And you'll see that in your homework as well. So the example we have here is working at a bank. So imagine this example here, and we've got cars going through these lanes here, and so we want to be able to model this process. Cars arrive, they spend some time here, they leave. There's resources inside the bank that we can't see. There's a number of tellers and things like that, and so on. And so this is our conceptual model. So we say, so this is kind of like for input modeling report. This is like a type of diagram I want you to sort of be describing in your input modeling report. We're modeling a bank. We think that the input models, the random variables coming in, are going to be the kind of encounter rates and the service times, our decision variables, how many tellers we have, what the mean service time is. And so the idea is maybe with training, you could change the mean service time, and how many lines we have. And then I've got my simulation model, which I haven't built yet. So again, think your input modeling report. You haven't built this yet. But you imagine once I build it, I'll be able to measure how often the tellers are utilized, their utilization from 0 to 100%, what's the average delay per customer, and what's the maximum line length. So, so these are things these are the things that I want you to be thinking about coming out of your input modeling report. This is what we have to build. So input, model, output. So this stuff we know how to do now after the previous lab. This is our input modeling, where I've got data from the arrivals and the service times. I'm going to fit good distributions to those. That's my input modeling. So my validation step is, let's look at the outputs that come out of the real world and compare them to the outputs that come out of my model. The data I get out of the real world will not be used when I program the model. It's only used afterwards to see if I've done the programming right. So that's you're going to take these data, but you're not going to use them when you actually program until you get to the calibration step. So that's the kind of important thing here. You're not going to program in an average delay. You're going to calibrate your model so that your model, when it's properly calibrated, produces an average delay which matches the real world. So how do we do that? So I'm going to gather a system response variable from my simulation and from my real system. So my simulation values are going to be Y, my real system values are going to be Z, and I make sure that, for example, all data is collected the same period of the day. And so I want to make sure that my bank system, I know the 9 to 10 hour works very different than the 4 to 5 hour. So I only collect data from the 9 to 10 hour or something like that. So then I can compare my simulation outputs. So if I go back Y2, that's my average delay. So I'm going to say, let's look at the average delay outputs from the simulation model and compare them to the actual average delay of 4.3 minutes. So in the real world, it's 4.3 minutes. let's look at my simulation output. So I have a null hypothesis. So under the null is that my model and in the real world match. Under the null, I would expect that the expected average delay is going to equal the average delay that I've gotten from the real world. So I'm going to take replications from my simulation and use a statistical test to test this null. So I do 6 reps for my simulation. Why 6? Well, this is where that power analysis would come into play if we did this rigorously. And so if there's a lot of variation, we might need more than that. If there's not that much variation, 6 might be enough. But then for each replication, I might do a verification step. And so I make sure that my inputs are doing the things I expected them to be. But then for validation, I measure the average delay. And what do I do with that? I put it in a table. And so here are my 6 reps. And then I've got for verification, I want to make sure that the arrivals per hour, is this consistent with the distribution I picked for that? I could go and check that. Is the service times, is that consistent with the distribution I picked? I could go and check that. If either of those were wrong, I know I did something wrong in ARENA, easy fixes. That's the verification step. But then I look at the average delays here coming out of the model, and it's out of the simulation model, and I now need to test them against the hypothesis that the population mean is 4.3 minutes. And so that would be a great thing to use a t-test for. So I am going to take my average mean from the simulation and compare it to the mean that was in the real world. And so I'll talk a little bit more about the history of this, the t-test and how it relates to Guinness brewing next time. But the basic idea here is that I've got this calculation, which we'll talk about where it comes from as we move on. But this statistic here helps me test whether the average of these things, which is this 2.51, whether it is a reasonable variation away from the 4.3 that I'm expecting. So that 2.51 will go into here, and that 4.3 will go into here in the effort of testing this hypothesis. So we call this a one sample t-test. A lot of people get confused about this. Well, how is it a one sample t-test? Aren't there 6 samples? But the thing that goes into the statistic is a single data point, and that is the average that comes out of that. So I don't put all 6 of these data into the t-test, I put their average into the t-test. That's why it's called a one sample t-test. And then I'll put the hypothesized average over there. So if my data are independent and drawn from a normal distribution with this hypothetical mean, then I would expect under the null hypothesis that this statistic, this t statistic, would look like a student's t distribution. And that's how I can check to see if my deviation is off or not. And so what I'm going to do is calculate this value here, and I do a 2-sided test, meaning that I care about variations on either side of the mean. And if that variation that I measure with this thing is larger than my critical value on either side of it, so I take the absolute value, then I'm going to reject my null of the 4.3 and say there's something wrong with my model. So we go and we do that, and we plug in the 2.51, that's that average that was out of that table. We plug in its standard deviation, its sample standard deviation into the t value, we get a value of 5.34. So that 5.34 is, if I look at my critical values, my critical value for this is way less than that 5.34. So this tells me that I'm actually rejecting the null hypothesis that my model matches reality. There's something wrong with my model. My model is not validated. So I then have to go and think about, for one, can I trust these statistics? And so I might want to go back and make sure that the data out of my model are normally distributed, because if they aren't normally distributed and independent, then I can't use a t-test. But let's assume that they are. In that case, there's really something wrong with my model. So I have to go back and I say, what did we get wrong with the model? What were our assumptions that were in our head when we did this model? Well, we said that when a car is waiting behind another, there's no delay between one service ending and the next beginning. And that could be a bad assumption. It might take a while for one car to get out of the way and the next car to come in. But when we looked at the data, it really looks like the cars are kind of like train cars, that they one goes out, the other one comes in, and it's not something we need to worry about. So what else could it be? Well, we also assumed that when the car arrives at the window, if the window's available, the service begins immediately. Now, after gathering more data, we found that this is incorrect, that a bunch of times cars pull up to the window and service doesn't start for a while. And why is that the case? Well, it turns out that the teller is also handling walk-in customers that we didn't see. So there's a whole nother group of walk-in customers coming into the bank that are taking the resource away from our drive-through customers. And so we say, okay, well, we need to model them. We need to now also have as an input the walk-in customers. So we're gonna have to go back and rebuild our model so that we have arrival and service data on the walk-in customers too. Even though we're not modeling the service of the walk-in customers, they are having an effect on our drive-through customers. So we need to go back and get data on them and rebuild our model. So we go back and we do that and we rerun the model. We get this out here, and now we find a sample mean of 4.78. So with our sample mean of 4.78, sample standard deviation of 166, and our hypothetical mean of whatever it was, 4.71, we generate the T statistic, and it's much smaller. And so this gives us some confidence that we won't reject our model. So we can't quite accept our model, but at least we don't have enough evidence in 6 samples that our model is worse. If we ran 1,000 samples, I can guarantee you we would reject this hypothesis, because this simulated model is going to be different than the real world. But if the more samples we run, we'll detect a smaller and smaller difference, and eventually we will reject it. So at least for 6 samples, where this amount of difference doesn't cause a red flag. So that's all I'm kind of saying here. In order for us to really be able to confirm, we need to calculate the power of this test. And so, so that's how do we do a power analysis. And so I'm going to go through this a little bit quickly, but I've got an example online right underneath the homework. This is, you have to do a power analysis for the second part of the homework, and that's what this is all about here, except you do a power analysis of a paired test. So with a power analysis, again, we went over statistical power, it's the true positive rate. And so in order for me to generate a power analysis, I have to calculate, I have to have some notion of an effect size that I want to be able to detect. And so the effect size, there's this little normalized effect size I'm calling delta here, which you can think of it as a kind of threshold amount of difference that you want to detect that's normalized by the standard deviation of the system. So if you want to say, I want to be able to detect differences that are this big or smaller, or I'm sorry, differences that are this big or larger, so there can be any differences less than this I don't care about. The differences bigger than this I do care about. That difference that you want to detect, you divide it by the standard deviation, the amount of variation in the system, and that gives you the so-called effect size. And I can then look back in the operating characteristic curves in the book, and actually then from there, figure out how many samples I need for a given statistical power. So if I say the minimum detectable difference is, I want to, $4 in profit. If I divide that by my standard deviation in profit, which might be $2, then 4 divided by 2 gives me a 2, and this delta I look up in the back of the book will be a 2. So I think I've got these operating characteristic curves. So what I would do is I go to the back of the book, and they're going to have these for different alpha values. So I've got alpha equal 0.05 over here, alpha equal 0.01 here. I care about an alpha of 0.05. So I zoom in on this OC curve, and then I say, all right, what statistical power do you want? 80% is the gold standard for statistical power. 80% power corresponds to a 20% beta value, type 2 error rate. So I look at type 2 error rate here, and I then look at what my effect size is in terms of numbers of standard deviations. And if I want a 2 on my effect size and a 20% in terms of my type 2 error rate, then I know that I should take 5 samples or more by looking at this. If I take 4 samples, I'm not going to have enough power. 5 samples, I'm going to have plenty of power, because this is the 5 sample line. So wherever the effect size is, you meet the desired beta type 2 error value, and whatever line you land on, or the line less than that, that line tells you how many samples you need for that statistical power. So that's kind of a rough estimation. I'm going to stop there because we're at time. But are there any quick questions about this idea? So I'd interpret this plot. You calculate, I give you a minimum detectable size. You normalize it by the standard deviation of the system, which you've estimated. That gives you your effect size. I give you a statistical power, 80%. You do 1 minus that, you get 20% error. And then you look at the OC curve and you figure out how many samples you need to meet those 2 constraints. And that's what you'll practice on your test or on your homework, but with a paired t-test. All right, well, let's stop there. I've got an example of that again online, and we'll pick up with this next time. There's only a couple of slides, just a paired example, and we'll do the last attendance question here is just going to be what is the gold standard for statistical power? What do we usually require in statistical power? What is the, like 0.05 is the gold standard for type 1 error? What are we looking for in terms of statistical power? It's another percentage. I just sort of said it. So what is the usual expectation for statistical power in percentage? And that's all I've got for you. So I will see you Thursday, unless you have some questions that you'd like to come up with after class here. Hi. Sure. Let me end here, and so online, that's all I got for you. So if there's no questions lingering, I will see you all Thursday, and I'll be about to stop the recording.